Differential length in the cylindrical coordinate system. Consider point P1 with coordinates r, phi, and z in the cylindrical coordinate system. To find its differential length, each time we increase one component of this point by a differential amount, and a new point results. The change in length produced by the increase in that one component defines the differential length among that particular direction or that particular axis. Suppose we first change r. Point P2 is obtained with coordinates r plus dr, phi, and z. So, point P2 shares the same phi and z as point P1, and only its r has changed. We have increased point P1 by an amount dr, while phi and z remains the same, and only its r has changed. This is how point P2 is obtained. Now, if we define a vector from P1 to P2, vector P1, P2, its magnitude, as shown in the figure, is simply dr. That is, the length traveled from point P1 to point P2 equals the change in r between these 2 points. The direction of vector P1, P2 is along the unit vector a hat sub r. So we can say the change in length along the r direction equals dr times a hat sub r, denoted dl sub r. Now, let's turn to phi. Suppose we increase the phi coordinate of point P1 by an amount d phi, giving point P3. So r remains the same and we increase phi by d phi. That is, we go from phi to phi plus d phi. Z also stays the same. This gives us point P3. Now we consider a differential vector from P1 to P3. We want to determine the length of the arc traversed. This is the angle d phi, and this is also the magnitude of vector P1, P3, or in other words, the distance from point P1 to point P3. Since this distance is approximately the arc length, subtending the angle d phi, and by the standard mathematical relation arc length equals radius times angle, we get r times d phi. This is in fact the length of an arc or a portion of a circumference. If the phi were a full circle, that is, if our change in angle were 360 degrees, this relation would give 2 pi r, the full circumference of the circle. But since here it is only proportional to d phi, this arc length equals r d phi, and its direction is along a hat sub phi. So dl sub phi in the cylindrical coordinate system equals r d phi times a hat sub phi. For the remaining variable z, which we previously showed in the Cartesian system, dl sub z equals dz times a hat sub z. Consequently, we added these three differential lengths together, dr times a hat sub r plus r d phi times a hat sub phi plus dz times a hat sub z. This gives us the differential length in the cylindrical coordinate system. We have shown that the differential length in the cylindrical coordinate system is obtained from this relation. Now consider a spring. This spring has a certain number of turns wound around a fixed axis. Assume the thickness or the diameter of the spring's wire is negligible, so that it can be approximated essentially as a line. That is, the thickness of the spring wire is very small. Place this spring at the center of the x, y, z coordinate system. The distance r here is constant, meaning that all points on this spring are at a constant distance from the z-axis. So dl sub r is 0 here. No change in r is observed at these points. However, phi varies from point to point, ranging from 0 to 360 degrees. The points have different values of phi. For this spring, the height of the points also varies. So dl for this spring equals dl sub phi plus dl sub z, that is r d phi a hat sub phi plus dz a hat sub z. Now, please observe this shape. If we consider this within the coordinate system, you can see that r for the points forming this shape are not constant. Phi also varies for the points along this contour. They can have different values of phi, but all of them have the same constant z, remaining essentially within the xy plane. So dl sub z here is 0. So we can say dl in this case is the sum of dl sub r plus dl sub phi, that is dr a hat sub r plus r d phi a hat sub phi. Now, let's move on the standard differential surfaces in the cylindrical coordinate system. The first standard surface we consider is the constant r surface. That is, the points on this surface must maintain a constant distance from the z-axis. Consider a point with coordinates r, phi, and z. In generating this surface, we are not permitted to change the point's distance from the z-axis. However, we can give it an arc, changing it along the phi direction. If we change it full, a circle is formed. We can then introduce a change in height along this circle, and ultimately this yields a cylindrical shell. Now, if we view this shell from above, we see that all points have a constant radius and a surface is perpendicular in the direction of positive or negative a hat sub r. Therefore, for the cylindrical shell, the S equals plus or minus r d phi dz times a hat sub r. So the first standard surface, constant r, is in fact a cylindrical shell. The next surface is the constant phi surface. Again, consider our point. Now we can introduce a change in length r, a change in height z, but we must now introduce any change in phi, that is, no arc around the z-axis. So we introduce a change in r, a line is essentially formed. If we then give this line some height, a rectangular shape results, like a door. If we look at the points of this door from above, we see a line where every point have the same angle related to the x-axis. The surface normal is along the positive or negative a hat sub phi direction. Therefore, this constant phi surface hinged as it were along the z-axis has a differential surface element of plus or minus dr dz times a hat sub phi. Finally, the last surface, constant z. Again, consider the point. Here we cannot introduce any change in height, but we can change the point's distance from the z-axis and introduce an arc around the z-axis. So we create a line by varying r, then rotate this line around the z-axis to form a disk. Now, if we look at disk from above, we observe a change in length and a change in the angle phi dr and r d phi. Its direction is along the positive or negative a hat sub z perpendicular to the disk. Therefore, for this horizontal disk, ds equals plus or minus r dr d phi times a hat sub z. So we have now defined three standard surfaces. The constant r surface, representing a cylindrical shell around the z-axis with its differential surface element as given, the constant phi surface hinged as it were along the z-axis, and finally the constant z surface, or the disks lying on or parallel to the xy plane, which we call horizontal disks. The ds for each of these has been written beneath the corresponding surface. Now, for each of these differential surface elements, based on the given figure, you must determine the range of variation for the relevant variables. For example, for the cylindrical shell, over what range does phi vary on the surface? Since we currently have a complete cylinder, naturally phi ranges from 0 to 2 times pi. So sections of these surfaces can also be considered, in which the ranges of the variables phi, r, and z are altered. It is therefore not necessary for all these variations to always be complete. It is not necessary for our horizontal disk to always range from 0 to 2 times pi. It could instead be cut at a middle, forming a sector, that is, a slice taken from this disk. In that case, ds remains ds sub z in form, but its bounds differ from those of the full horizontal disk shown here. Now, the differential volume. To obtain a differential volume, we must introduce a change in all three variables. that is produce a change in length along each direction and multiply the three length changes together. Suppose for simplicity we take a point on the xy plane with coordinates r and phi. We create a small dr, a small change in length at this point. Then we give this dr a differential height dz. In doing so, a sort of door hinged along the z-axis but not attached to the axis itself is essentially formed. We denote the surface thus created, ds, as dr dz. Now we must introduce a change in length along the phi direction as well, that is multiplied by r d phi. Therefore, the differential volume in the cylindrical coordinate system equals the length change dr times the length change dz times the length change along phi, giving dr dz r d phi, which is conventionally written with r placed first in order r dr d phi dz, though in fact this r belongs to the dl sub phi term. Now, what shape results if I also introduce a change in phi into this differential surface element? Such a volume is created, where z ranges between 0 and h. The cross-section spans from A to B, and phi, in this case, ranges between phi 1 and phi 2. So you can see that this is a portion of a cylindrical volume that has been sliced along the phi and r directions, and of course it could also be sliced along z. Consequently, the differential volume in the cylindrical coordinate system equals r dr d phi dz, and based on the given figure we must determine the range of variation for our variables. So we have shown that the differential volume is r dr d phi dz. For a complete cylinder, we still have this same differential volume. Now let us specify the ranges of the variables. For example, z ranges from negative h to h. To determine the range of r, we look at its cross-section. We see that for a solid cylinder, r ranges from 0 up to the radius p. Phi in turn ranges from 0 to 2 times pi, since the cross-section is a full disk. This gives us the ranges of the variables for this cylinder in the cylindrical coordinate system. Now suppose we hollow out this same cylinder, it becomes this shape. Naturally, this requires a change in our variable. Z remains unchanged, still from negative h to h, but when we look at the cross-section, we see that r no longer starts from 0, it now starts from same non-zero value, say a. So our ranges from A to B, our ranges of rotation or phi remains as before. Spanning the full cylinder, so phi here ranges from 0 to 2 times pi. Thus you can see that by changing r, we were able to specify the bounds for this hollow cylinder within the cylindrical coordinate system. Now, suppose we cut this same hollow cylinder in half and keep the right hand half, we arrive at a shape like this. Now, is its differential volume the same? Yes, its dV is still r dr d phi dz, only the bounds of the variables are updated. Z still range from negative h to h, unchanged. But in the cross-section, r ranges from A to B, the same as in the previous hollow cylinder. Here, however, phi ranges from 0 to pi, since we have kept the right hand half. Had we kept the left hand half instead, phi would range from pi to 2 times pi. Now, let's take this same hollow half cylinder shape and make another cut, a 90-degree cut within it. We arrive at a shape like this one. Now let's write out the range of the variables. The height still remains the same from negative h to h. Looking at the cross section, r still ranges from A to B, but phi is no longer from 0 to pi, it now ranges from 0 to half pi, that is 90 degrees. In this way you can see that for a cylindrical volume, through various cuts, introducing changes along the phi and r directions, and of course z as well, you can generate other shapes from within this cylinder in this coordinate system. However, the differential volume remains the same,